All right. Thanks everyone for coming in. We'll get underway now. All right, it's about starting time. Okay. Thanks everyone for coming down to our semester 1 Foundations for Algorithm Revision workshop. Very glad to have you here. This workshop is going to go over quite a few things. Hopefully it's helpful. Hopefully you get some practice in. Hopefully you're able to meet some people who will help you study and get prepared for your exams. At the end of the day, if you walk away feeling a little bit more confident, that's a win. Okay, so just some housekeeping very quickly. My name is Avjay. I'm the current education director at CISSA. We just want to have a short disclaimer before we go into this workshop. We will do the utmost to ensure that all the content in this workshop is accurate, reflective, and does benefit your exam preparation. However, we cannot say that we are endorsed or that this content has been endorsed by the current teaching team at the University of Melbourne, and there is no explicit guarantee that that all the content on this presentation will be the content on the exam or necessarily reflect the nature of the exam beyond what has already been communicated to you by the teaching faculty. Okay. That being said, we can get into more fun things. We are CISSA. A lot of you probably already know us, but for those who don't, we are basically the premier computing society at the University of Melbourne. Every week, we run social events, educational events, industry events, and a plethora of more things that aim to connect the student community here at Melbourne and provide you with the education and upskilling that you need to succeed not only in your subjects, but hopefully in your professional, social, and academic lives as well. So right here, we've got a link to our link tree. I'm just going to grab our thing out of the way of that, so you can scan it if you'd like. That has access to all of our links, access to past revision workshops, our newsletter, and links to sign up to become a member if you would like to hear about what we get up to on a week-by-week basis. Membership's completely free. No obligation to do anything beyond sign up to be a member and hear about the things that are going on. We'd love to have you. But all of that being true, we'd like to get underway with the workshop now. So Harrison has very generously donated his time. He'll take on over from me from just a second. And he'll be walking through today's workshop. So that being said, we'll get underway. Sorry, this is just a quick summary of what I've just said. We organize revision workshops for nearly every single major computing subject, with the roster changing perhaps slightly bit by bit, but we try and cover all of them this year. This year, we're running 7, hitting all of the ones that which we get the most requests for. And at each one, we aim to have only experienced tutors, both past and occasionally present, come in. Of course, all of them being in an independent capacity outside of the teaching team. All right, so that's the end of me. We'll welcome Harrison to start the revision.
Okay, so let's get started. First mistake is giving me free roll to create the slides. Basically, here's us at the start. We're cooking with algorithms, and this is you, small, smooth brain FOA students. But anyway, that's just a little bit of fun. Let's get started. I will say, just preface again, look, I'll try and teach to the best of my ability and overview what I can. The subject has changed a little bit every semester and every year. I did this subject actually in 2021. So even since then, despite algorithms not changing that much, small things have changed, such as certain algorithms added, removed, content, and that sort of stuff changed. So I'll try and do the best what I can. Essentially, we'll just have a quick overview of a few concepts. And then after, at the end, there'll be an extra hour and a bit more for more questions. And that's where really, hopefully that'll be where the most value is in, because we can actually communicate with that as well. Because again, I'm basically trying to base this content on what was most difficult in the past. And I've had to make a few last minute changes due to some course changing and that sort of stuff as well. Super basic stuff just to remember as well, different things such as loops and data types as well, understand the values and the ranges. They are pretty easy points to get on the exam if you have questions like that, just understanding the different values. They can be stored based on an int, long, float, double, character, that sort of stuff, as well as maybe the different data sizes, which will become relevant later. Understand as well the difference between for loops, while loops, that sort of stuff. Again, good to know it's basic things, but it can just give you that bit further and a bit of easier points, and also give you a bit more confidence in the exam, because it's so easy to get so worried about all the harder stuff, such as the different for example, algorithms and that sort of stuff, just make sure you've got the basics down and you can build upon the other stuff, even if, yeah, just as a way to like help focus on that. Now, things like pointers are simultaneously probably one of the simplest and hardest things about it. Understanding a few different things, such as they all take up around about 8 bytes. You've got pointers and then addresses to them and references to them, dereferences, a bunch of funky stuff like that as well. And in addition, also the memory itself, that sort of stuff. And where was the other slides? I'll get that later. But essentially just understand you've got all the different data types, that sort of stuff, how it points, references, and tons of stuff with memory management. They are really unique about C. That's what makes it special. Lets it do a lot of cool things, but also makes it hard because the problem with them is that often we manage them and are working with them, and that makes it very hard. Now, if anyone here would like, I'm happy to do a quick demonstration of a bit of how pointers work and maybe some of the use cases. But essentially, if anyone here wants to volunteer for that. Do we have any volunteers? You'll get bribed with chocolate. Okay, I'll get you up. By the way, you won't be asked questions. Your job is very simple. You just need to hold this card. Okay, now we need one more volunteer. You also get a free chocolate. Okay, your job is very simple. You're going to stand here and essentially put your arm out and point at this person here. So this is one way to think of pointers as well. Remember, when we think of pointers, you've got, for example, the pointer and the value, in this case, P and X. Are they the same thing or are they different? I'll be waiting for an answer, yes or no. Doesn't matter. Or you can say, I don't know. So can we that a bit louder? Yes, they are the same thing, or are they different, X and P? They can be different because they're two different things. Oh, sorry, are they? Never mind. Yeah, essentially just understand that these two things here are different memory addresses and we reference and point them to it. So these two here, they are not merged together as one thing. They are two different living, breathing entities. They also have their own memory data and that sort of stuff. One thing that might help to think of just different thing about pointers and that sort of stuff is, you know how these are all the same size, integer pointer, string pointer, book pointer, and that sort of stuff? Is the integer, string, and char, sorry, integer, char, technically strings, just an array of char. Are they all the same size? Is integer, char double? Are they all the same size? No, they're not. But pointers are. Does anyone here want to have a guess why? Yes?
They're all pointing for memory address, which is the same as ours.
Exactly. So that's why. So even though these are the same things, here's a little value on here. It could be different. It could be a king, or it could be a 2. Essentially, these could contain different sizes, but at the end of the day, they're just different objects with a memory address behind it. Here's a little mask up that puts in front, but there is a whole thing behind it, essentially a memory address. Basically, it is a hexadecimal value. You don't need to worry about what the hexadecimal values are. Just understand that you've got the value that it's stored in. Keep in mind, though, one thing I just want to clarify. I don't know if you guys cover how much this matters in FOA yet, but essentially how you've got multiple hexadecimal values and the specific way that you manage memory as blocks of units. Do you cover much of that? I just want to go out of scope because this stuff will be covered later in 3rd year, definitely. So I actually don't know if it covers much, but if not, don't worry. But essentially, yeah, probably beyond that. But essentially just, you've got your different values, you can store them, and there might be multiple blocks to store, for example, a double, but essentially we point to the start of that value and that array or that memory address, and we point to it, we store that. So a pointer is essentially just a way to say, hey, we're going to store a hexadecimal data type, opposed to an integer data type. A pointer just reference hexadecimal in some sense. That's, yeah, pretty much demonstration there. I just want to show that pointers and the value itself are different things, different beings. They're the same. Take a chocolate, whatever you want. But yeah, essentially, I just want to explain that they are different things. They point to values and that as well. Obviously, there's things where you reference it, dereference it, void pointers as well. I'll go into that a bit more detail in a sec. But there's the void pointer slide. But yeah, essentially just understand that the value, sometimes it might help to think of it as a pointer is just a hexadecimal data type, similar to integer or character or that sort of stuff as well. Part of the reason why you get into voids types is that you might not know the exact data type you're working with. For example, what's one of the most common ways that we use void data types? So that's actually, that might be out of scope. So instead I'll use a different example of voids, but so that might be a bit out of scope, but essentially just understand that void data types allow for a bit more usability and what you can use and polymorphic operations. Essentially just means more flexibility with it as well. Really important thing is you need to declare the data type that you will be working with. Essentially, that just means you need to state how much memory it'll take up. Part of the reason why that is because you've got the integer, the doubles and that sort of stuff. You need to say how much of memory you need to look into. Because, for example, how many bytes does a character or char take up? I'll give you, do I write it here? No, no, but we can say, which one of these values, give me one V that's a lot bigger in its storage, one V that's a lot smaller. And anyone here will get a free chocolate for answering. Yeah, so char and double, one's bigger, one's a lot smaller. You can see that, for example, sorry, I didn't write up the specific data, how many bytes it uses up, but you can tell that anyway. What chocolate do you want? Do you want a milk top, breaded frog chocolate, or caramel or cola? Take whatever you want. But yeah, understand that those are different, and part of the reason why you need to declare the data type of them is because it also tells you how much to look in memory. That, again, the memory management stuff, part of the reason I'm saying this is it kind of builds upon the concepts of going to, where was it? Sorry, I should have reworded, ordered these, but essentially memory management, that sort of stuff, where you've got the malloc and that sort of stuff, heaps and stacks and that sort of stuff, where essentially you've got the actual arrays itself, which contain data types, but then you've also got the pointers and data types itself. A big thing in computing is that you essentially build upon itself and makes things so that way they can work automatically or automata in itself. So the way you think of pointers and memory and data types like that is the same way as you may manage manually memory functions, and that's memory in terms of arrays and that sort of stuff as well, where you're just making new data types. You just abstract it away and just decide about how much you're choosing to abstract it away. I understand this also may be a bit more abstract. Again, happy to clarify with questions you want as well. But yeah, where was I going back to? Yeah, one thing to also just be careful about, and also a feature of working with pointers as well. Note when you're in scope and out of scope and how you can access the memory itself as well and where that matters. Where the name N, for example, that might not necessarily be the same because that's just the silly human readable one because we like clear things like this. If, for example, I told you access OX77FFFA0757DD4, who here remembers that? Yeah, so we use letters or like names and variable names and that sort of stuff to access in the future. Just understand that there are addresses and memory behind that, which is why you may want to use pointers. And an example like this is where you operate on a copy of N, and N and N are not the same. They are different variables. So be careful with that. You may be asked that on the exam, and understand that you instead could maybe use pointers to reference the memory address and modify the actual memory itself, as opposed to the variable name, which operates in scope as well. So again, if you see multiple functions in an exam question where they have the same name, that may be a question related to scope and memory management as well. I will say again, I don't know what the exam will look like. I don't know how it will be or the structure of that, but that's one thing that's, again, easy to trip up on as well and be careful of. Understand the memory management behind the memory addresses behind it, that there is a thing, and the abstraction is the names itself in C. But yeah, moving on with that as well. Again, just things about functions as well, where you can have void functions, int functions, they return a value, where you might not necessarily need to return a value with a void, and also understand the basic structure and how you can use pointers in the actual function itself as well, and that sort of stuff as well. Just again, understand how that works. I'm not sure how much of an emphasis it is for you guys, but just argc and argv as the arguments in the main. Actually, it's probably not. When we took the subject, they put a really heavy emphasis on that, but I don't think it will be as relevant now. Just curious, how much do you guys cover in big O notation and time complexity? Yeah, so, okay. Essentially just understand the growth rate of these. You've got this big, that's not super clear, but essentially for people in line, you've got this big scary equation here. Doesn't look that scary. It's not as bad as it looks. And you also have the big circle. All these equations here essentially just means the growth rate. Let me go back to this. Can you see the cursor here? Yeah, nice. Okay, that makes things better. Essentially, just understand the growth rate of this and how it works. Essentially, here's an example. Algorithms and that sort of stuff take up computational power and time. You've got little small computational things, or you've got big chunky algorithms as well for the computation thing as well. Essentially, n is just nice and smooth. If 10n takes up 10n time, but for example, operations takes up that unit. Note that this is an abstracted method where we just try to understand it regardless of the specific computer. For example, does anyone here have a really old laptop? Okay, nice. Your laptop may not, and this may be just a guess, may not be as fast as a supercomputer that I know there's a few data centers nearby in forget where it is, Mount Waverly. There's a few data centers there, for example. Those supercomputers there, just a guess, are probably maybe a touch bit faster than your computer, right? They'll run things faster, but an algorithm on that computer will take this much based on n steps, might take this amount of time or operations, as would, let me rephrase. Regardless of the computer, the actual computational time will be equivalent. And this is how we measure that here using this set of operations. One thing to remember as well, if you've got On and On log n or On squared, if I've got, for example, n plus 4n plus 2,462,000,000, or I just have n log n plus 3, which one's bigger? Does anyone here know which one would be bigger? So pretty much just if I add like n plus 4n, or can even drop the 4n, it doesn't matter, plus 4 billion trillion million, really big number. And then for n log n, or let's say n squared, if I just had n squared plus 3, which one would be bigger? It would be n squared, sorry. Yeah, the second one, n squared, because we always remember to drop the actual additional numbers, then the constants, and that sort of stuff, such as, for example, 4 billion trillion, whatever. In real life, things are a bit different, but this is a bit more abstract. This is going to a bit more mathematical and computational theory. And this stuff here is just the introduction to that. It is a bit more abstract, but it's just a way of understanding operations and looking at computational operations in a more abstract sense. It's something where I'd recommend mainly just understand the difference in time of how long it takes and just understand which order operations, n squared, n cubed, 2n, are pretty simple. It's pretty easy to remember that. But n log n and log n are a bit harder to know as well. And this probably isn't the best graph. Does this have the internet, right? Can I go to Desmos? Let me try something. Wait, where's the internet? Let me go to a new window so I don't. Just something to note as well. Just open. As well is there are things where even at a small scale, this algorithm may be better, but in general, we consider it to be larger because after infinite amount of time, it grows incredibly large. Even at a smaller scale, it may technically be faster. And also one thing just to note for fun as well, this I can almost guarantee will be out of. There we go. I can almost guarantee this will be out of scope, but big O is just one of the notations. There's also big theta and big omega, which also determine bounds and other things. You don't need to know that for now, but it will be relevant later just as a fun fact. But again, big O is used to represent order of growth after an arbitrarily long amount of time as well. So yeah, just note down the length of that and note that log n is faster than n, which is faster than n log n, which is faster than n squared, and so on. Good to know, and that. I'm not sure if you guys will be required to look at an algorithm and understand the time complexity of that, but if you are, generally the easiest way to tell a for loop inside of a for loop operate on the same array. For each item in that array, it turns from an n object to a 2D object. For example, I might try and draw on the whiteboard, see if that works. Yeah. Which one was that? Okay. Let me just quickly try this because it's easier with a lot of things just to like draw it and explain it. But this is just an example. For loops generally easiest. Let's just say you got this for loop, this array. And if you operate it on each point of the array, you operate it on at least once. That means that for example, for I, for j, and then we operate on the array. That means if, for example, I is set to 0, and then we operate on all items in the array, there could be tons of different algorithms that do that. We will then, I should have drawn this here. We'll then operate on the array once here, going through it, and then the next time we'll do this here. This is kind of an example of how it might work. And again, it all might be the same because we're not making any changes in that, which let's just say this here is n. N, how big's this array? Or the number of operations we do? Yep. But if let's just say, for example, we're operating on the array and maybe we're changing the length of that sort of stuff, where instead it halves up here, and let's just say it goes up here. Do you know how long the length may be for now? This is a bit harder, so don't worry if you're not too sure. But essentially just understand that the length halves and shorter, so it operates in maybe, for example, instead of like that, maybe a logarithmic scale. Oh, also don't forget, log is always assumed to be base 2, pretty much all the time in here. But understand that the length is changing, so that maybe involve a logarithmic scale. For example, if it's halving, just as like a general arbitrary rule. Again, it's not always like exact, but it usually helps close enough to know just as like a hint with that. Oops. But yeah, that's super basic overview of that. How are we going for time as well? Okay. But yeah, essentially just understand that where it's maybe n squared or log n or n, just pay attention to the array, the operations, and if need be, just draw it out and kind of like try and count it. Patterns aren't always the best way, but it can give you a close enough reference. Oh, other thing, also don't forget, if you're working with memory as well, malloc free, every malloc should have a free as well. Working together like that, understand the difference between stack, which is local variables, and heap, which is where dynamic memory. We can dynamically modify, change things, that sort of stuff as well. Size also needs to be known at compile time, which essentially just means when it is compiled or created, the algorithm. And yeah, essentially just, again, you're operating on the addresses in the array. Again, if you'd like, happy to go over more detail with specific examples. I don't really have much on me right now with your questions, but it might be easier with that as well, because again, this is abstract stuff, but just like kind of review the difference between heap and stacks and that sort of stuff as well. It's, yeah, it goes surprisingly deep into this stuff. And if you guys continue doing CS, you'll be dealing with a lot of memory stuff all the way up to your third year and learning how it works even deeper. So that's a fun fact. Sorry, that one there. Don't know off the top of my head, so create that. Yeah, so I know I was here. I made some of the slides, not all of them. It's kind of a legacy of like 3 or 4 different people. I'm not too sure. They probably had an example when they made it, but integer type, but yeah, to be honest, I haven't really prepared much for that. That was a few people have made these slides over time, and I'd taken over this time making some changes. So yeah, I don't really have much planned or relevant for that. So I guess if you want to play around more with that and figure that out, put it up and see. But I don't have much prepared right now with that. But yeah, again, they probably just were working with malloc memory, that sort of stuff. Yeah, apologies for that. It's, yeah, we'll make changes to the slides every year, and it's usually different people presenting. So apologies, I haven't actually prepared much for that. That's kind of like a legacy and artifact of the last person. So don't worry too much about that. But yeah, again, just understand the actual managing memory and the difference between, oh, also one thing to make sure as well, memory leaks versus seg faults, where you can have the difference, where there's maybe too few. So every malloc should have a corresponding free to like free up the memory and the addresses and that sort of stuff with the program. Too few leads to memory leak. Too many can lead to seg fault, where you're maybe trying to free memory that you don't technically have access to, because each program segments how much memory it can have. That's based on more things related to like the operating system, environments, and that sort of stuff. Don't need to worry about how it determines how much memory the computer has. That's, again, out of scope for now. But just understand that, yeah, essentially you can have memory leaks, seg faults, where they can occur, because you may be asked what type of error is this, or maybe where can a seg fault occur. But yeah, basic things on data structures, building structures, that sort of stuff. Essentially, you've got structs, that sort of stuff, type defs as well. Does anyone here want to have a guess at what a type def can be used for? You can just read the answer off here if you want. Yeah.
When you make a data type that you want to just refer to again and again.
Yeah, literally just that. So for example, by the way, if you ask a question, you can just say, I don't know, and you'll get a free chocolate anyway. I want to get rid of these. But yeah, essentially it's just a way to like rename a variable thing. For example, you could type an int and call it int, but instead of int, I want to call it number for some reason. And you can define it as that, essentially almost as if it's like pointing to a data type. It's not a pointer, but if you like to think of things in pointers, you can think of that as you change the name of it to be this because you want to call it differently. Essentially, for example, this example here, type def struct node t. The node t can be at the start or at the back, but essentially you may want to, for example, call it the node type is the data type. So essentially you've got, let me use my cursor here, sorry. So you've got this here, struct node, and you might wrap it in a type def node t. So then you can define it, define it later as the node data type as well. Essentially, it's just a way to rename data types because you're lazy and you don't always want to write the longer verbose data types, or you just want to save time or make it more human readable. There is very much an argument against how much things should be human readable versus how much things should be pure computational. It's kind of like a battle, or that's a fight of how readable versus how computationally perfect it is. These here are for humans to understand code and make the changes we need, type defs and that sort of stuff. Structs are essentially just structures, scaffolding that allow us to define more data types. For example, if you want to store person, age, and some generic stuff like that, instead of making person 1, age 1, person 2, age 2, person 3, age 3, person 4, age 4, instead, you can just have a person data type, struct, and essentially just have that contain that whenever you reference person. It could also be, for example, like the suite of cards, the suit, sorry. For example, instead of doing ace, spades, diamonds, that, instead of doing ace, 7, diamonds, 7, blah, blah, blah. So you can essentially change it to be a struct, so it's just a bit more nicer and human readable, so that way you can modify it and work with it easier as well. Others and where structs come into useful as well is linked lists. We just create nodes that point to each other. This, for example, where they can be doubly linked single, have a head and a tail, essentially just points to the next node in that. For example, these here will be pretty important, and that's a really useful data type as well, and allows you to traverse a bunch of different sort of, I guess, arrays in some sense that can contain data inside of it as well and reference the next data point. Kind of building off like linked lists and that sort of stuff. In some sense, you've got a few other data types such as stacks and queues. So for example, a stack is last in, first out, or LIFO, where essentially it just stacks on top. So for example, you have a bunch of cards, you add them on top, you do that. So the last in is the first out. So essentially it's on top, it's out on top, that, oops, that, and then if you change it like that, whilst a queue is like flows through, people online might not be able to see as well, but essentially it's just as the name applies, a queue where if you're first in, you're the first out in the queue, whilst a stack, you just stack them up on top and take the top one out. And yeah, understand the elements of push and pop, and also queue as well, and dequeue, but also the way you've got priority queues as well, which is sort of a bit more arbitrary, where you may queue up, but then each value has an assigned priority, which that gets a bit more complex just in its structure, where it may not be the first in, first out, but it can change things as well and how it works. Do you guys focus much on hash tables this sem?
Yeah. Yes, hash tables are in scope.
Okay. Yeah, probably for it's something where I don't really know how much is in scope or not. But yeah, essentially just understand that hash functions essentially take an input and throw it at somewhere in the output. For example, picture all these tables here. Does anyone want a Freddy Frog? Free Freddy Frog. No one wants a Freddy Frog? Okay. For example, you take in the number, I decide where to go, arbitrary outside this table by sheer coincidence, the person has their hand up. and we just, oops, sorry. We just throw it out there. Essentially, we have some algorithm, often mods, where we take in a number between 0 and 7 is a very arbitrary basic thing, and there could be maybe buckets of different groups there. For example, here, each table isn't in a different group. And there may be keys to reference it. For example, group, I might call this table 1, table 2, table 3, table 4, and that's a way to reference it. For example, if I know, for example, this here is people from CISSA, this table here is not, but it's like, imagine this, if I know that, I need to access a certain value, I can access it using a certain key and then going in there. Essentially, just it's a way to store data and way to actually manage it in a bit more efficient way, and also map it and access it faster as well. Look, I'm happy to go into more stuff on hash tables if you have any questions. Happy to, but truthfully, I don't know how much you'll be asked on hash tables, and I don't know the specific questions because hash tables get really deep or they can be very light. So if you want, again, happy to go over it after. Really, I'm just trying to go over it as a service level, and the really hour afters, hopefully, where the most value, again, will be made. But yeah, just revise hash tables, how they work, and if there's any slides or any questions that I can try and help with that. Dictionaries, sort of similar to hash tables, just a way to store different data. Essentially, just to understand that there are, within the dictionary, there are underlying data structures there, such as hash tables, BST, and sorted arrays as well. They each have the pros and cons as well. But yeah, again, pretty light level. Yeah, we'll pretty much go a bit fast through the algorithm stuff as well, because yeah, there's been a few changes that were made last minute, so I don't know how much will be relevant. So I'll give a super quick examples on that. Yeah, one other thing, priority queue, just understand similar to a queue, just with priority, so a bit of an extra element, priority on there, the starter here. Just to understand that we call these things names, but there's nothing stopping you from designing your own data structures, queues, priorities, data structures, algorithms, that sort of stuff. We just have specific names for certain categories of algorithms. Trees. I imagine you cover most of these trees or seen all of them, right? Yeah, given the fact that you're all, is everyone here CS students, right? Sorry? Yeah, I'll go on. But yeah, if you're all CS students here, just understand that these are probably the only trees you've ever seen, because you know you guys never go outside, but just understand a few different types of trees and categories for the trees. Full binary trees, complete, perfect, balanced, and degenerate or skewed. Personally, I think degenerate trees are kind of funnier. Now, a little bonus quiz here, and the answer is there as well. So a degenerate tree is either skewed all the way to the left or all the way to the right. So someone here give me a number. 3, give me another number. Give me another number, that's not 5. 9, okay, for example, if you had 3, 4, 9, you could structure it where, I wish I, wait, oh, and I can draw on it. I am so stupid. Okay, this is revolutionary. So we had 3, we could do this. Sorry, 3, 4, and 9. And what may this be useful for? What type of tree could this be? Yeah, they can also be multiple trees, can be the same category. So think of it as like you got all your different trees, and some trees can be in both as well. Just keep that in mind as well. These are not all unison independent things, but a degenerate tree, let's go green because I like green because trees. A degenerate tree might be like this. Now, this is the easiest chocolate you'll ever get. What is this data structure a degenerate tree equivalent to? And the answer is up there. Someone who, have I given you a chocolate? Okay, what do you want? We've got three options: chocolate, the koala, Komodo koala, or milk top. Good choice. Do we have any left? They're popular. Yeah, there you go. Essentially, just to understand that they are equivalent to linked lists as well, where it can be like that, or it could be 4, 9, and just to understand the difference between them, and as well as the fact that some trees may all be the same structure. But yeah, there's also binary search trees, which allows you to actually search through the tree based on a certain structure. Yeah, not too sure how much they'll be covered, but just understand that it's a way to search and access data pretty efficiently as well. Also, just try to understand the height of the tree as well, what may be useful to n minus 1. So essentially, it's like logarithmic in the search because it grows at certain things like that. A lot of the concepts will relate and build upon each other. But yeah, algorithms, just a fun thing as well. If you guys have time and you're really like tired or bored, there's a bunch of like algorithms explained through Hungarian dances, which I found really funny. So I can put it up later if you guys just look up literally most common algorithms, Hungarian dance. There was like a whole ensemble dedicated to that. Yeah, KMP, this is pretty much the last thing I have. I'm going to be completely honest. Here, I had prepared slides on a few different algorithms, only to find that they are not covered. So KMP was very last minute, and merge sort as well, is which I'll put at the end. I think it may be easiest just to like go over an example manually with KMP. I've got a quick example up here, but it's something that I wasn't as fully prepared for as I had other demonstrations ready. But just understand with KMP, the key thing is that you can skip through, opposed to searching A, B, C, and move in the little value A, 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 until we get a match all the way here. Here. Essentially, instead of doing that, we're able to use a longest pre-suffix array to skip forward certain amounts, and that'll be important to figure out how to calculate that as well. But also, again, if you guys have any questions like sample exams on that as well, that may be a better example because, look, again, I want to mouse here. I haven't taken the subject in a few years. I don't know how you'll be questioned on KMP, so I don't want to set you up for the wrong information on that. I just want to be transparent on that, and I apologize for that. But yeah, just the main concepts are the fact that you've got the word, the string, the substring you're looking for, the string and the prefixes, and moving along the indexes. And that's the general idea. You may be questions on different aspects of that in the exam. But just as in a quick example of it going through, though I haven't added the longest prefix here. Suffixes array are another thing, only worth doing if there's many independent patterns as well. Few different ways to do binary search. Again, I'm not too sure how much of a priority this will be, but just again, if it is something that is ringing a bell, just note that down as well as just a bit of one of the more complex things that combine a few different topics as well. Also, sorting is that probably one of the final things you guys cover, right? Sorting, pretty much like the bread and butter of classic algorithms, essentially selection, insertion, that sort of stuff. There's lots of different ways to sort. Insertion sort is usually how you'll be working with cards, where you go through, you look for the number, you insert it in, then go through the entire array trying to find the next one. It's pretty slow, it's not very efficient, but it's the most intuitive and easiest to do, because I can almost guarantee everyone does insertion sort in their own time. Few other things such as quick sort and merge sort as well, where we pivot and do that. Easiest way to understand these, and heap sort as well. Easiest way to understand these is just do it manually. Look up a diagram like this, for example. Okay, good, it works. literally just write that out, write that algorithm, do it manually and compare, are your steps equivalent to this here? That will generally be the easiest and best way to do it. But just understand that with merge sorts, I wish I took it down, but essentially just understand that it's picking the elements, breaking them up, and sorting them in smaller areas, and then we merge and sort them together. Essentially, we break it up into a bunch of small bits of units of 2, and then merge them together. So it may work in, there may be a certain behavior here again involving the array, the amount that we're matching and comparing, may be changing. So there may be a certain value or operation, maybe a log, for example, involved in that as well. Yeah, that's also, do you guys cover much on binary twos complement, floating point, or IEE floating point representation, Mantisa, that sort of stuff? Sorry, yeah. Yeah, because that stuff, when I took it, very heavy emphasis. I think they've slowly got rid of it because they realized most people hate it, which is fair. It's vaguely useful in very niche problems, mainly useful for scientific computing where you're working with the values, but it's like really not, it's not that important in my opinion. Hopefully it's not important on the exam. I think it's probably a lot smaller. I'm happy to go over that as well if you want, but I don't think it's covered or as relevant now in the course. Again, don't quote on that, but again, happy to go over that after. But yeah, that's the main thing for pretty much everything here. If you want the slides, and there should be some practice questions prepared, right? So that should contain it, right?
So over here we have the URL that'll take you to a folder, the drive folder that will be accessible. In this folder, you'll find the presentation slides along with sets of questions from past exams. All of these questions, while not necessarily perfectly reflective of the current year's syllabus, will include content that has been kept on year over year just because it's the core bread and butter of the subject. Stuff like bunch arithmetic, stuff like function returns, stuff like basic pattern searching within strings. So both of those links, the QR code and the tiny URL, point to the exact same Google Drive folder. So just in case you want to take a photo of that, or you might type it down here. This will also be, I believe, personally, what we're going through in the next section.
Yep.
Yep. Right.
Yeah, that's pretty much that for, oops. Oh yeah, fun aside, unfortunately you guys don't have Alistair Moffat, but this one here, if you do, unfortunately, hopefully not take the subject again, you'll have this amazing man here who is a wonderful lecturer. But yeah, essentially, has everyone got that or? Yeah, so that's it, feedback as well at the end, but I'll let you do that as well. Okay. Oh, that there. Sorry, which one?
You go.
Yep.
So, here are all the things. So, if you like, just pick some questions.
Okay.
And give people time to go through them themselves, walk around checking on them, and then go through the answer on the whiteboard for the person. Cool.
Okay. Yeah, so we'll go through the questions now, or if anyone has any questions as well, happy to go over that. That hopefully will be where the most fair. Oops.
That's the section.
Yeah. Sorry?
That's the solution.
Yeah. This one is the questions.
So,
Okay. Yeah. There we go. What? Blank solution. What? No, this one's also solution. No, this is also solution. Wait, no, all the solution. There was a solution. Am I just blind? They will say solution. I'll sample here.
Mhm.
Okay, there we go.
Yep.
So let's see.
All good.
Yep, so I just need to check some stuff with work and it finally works.
So maybe just tell them whatever question you want them to start on, and then we can take the time together.
Fine, no, that's all right.
Okay, I'll get there.
Yeah, pretty much if you guys have got one of the examples here, if you guys want to get started on that or do your own study, and happy to go over any more specific questions there, should hopefully be more useful then. But yeah, pretty much now it's time for whatever you want to do or however you want to study as well. We've got, yeah, a few examples and answers there as well, if you'd like or find it useful. Yeah. Do you have any more?
Oh, yeah. So this would be a past question set that was released with the software. Yes, so this one is resources that the subjects given out previously. So these kind of questions resemble something like what you might get on an exam in that particular year. It may not necessarily be true this year, we can't quite guarantee that, but something that uses the same core skills might be. Yes, so these particular ones are the exam may not. These questions, I believe, came out during a time where the exam was delivered with pen and paper. Now I believe it's delivered online. So these questions came out during a time where the exam was delivered on pen and paper, so you'd have to write it down. Now I believe it's being delivered online. So okay, that's just if they change the service, which is, in my opinion, but yeah, Council, you can zoom in to the.
Yeah. Oh,
Question one. You probably give you guys like 5-10 minutes, or just walk with you.
so just curious, do you guys still use Grok? Use what, sir? That's so sad. You guys are missing out. Basically, in the old platform, there used to be these green diamonds when you got a question right, and people were addicted to getting the most green diamonds. So like, it was generally the best way to do questions because you'd be like, look at all these green diamonds I got. Like if you ask anyone that's like, I guess been at uni for a few years, they'll say they love the green diamonds. Also just do you have the answers on your laptop? I don't think I can connect on both my work laptop and personal because because I'm not a student anymore, I can't connect to the Wi-Fi.
Oh,
So I'll probably use your answers because I need to use my hotspot, but I'm using hotspot for work. So yeah, I'll need that. Yeah, also, if these questions aren't as valuable, I'm happy to just try and answer questions people have as well. Really, whatever's most value to people.
Yeah. What you're after?
Yeah. So it's like I realized that this is a nice snapshot. I just want to.
You can probably go through like an IDE, or if you want to go through like an online IDE.
Yeah.
Mind if I just
Yeah.
like online IDE and then you can just
Yeah, do whatever you want.
sorry, I need to
Oh, sorry. I might just do a check of how everything's going. Stuff.
you go. So this is something that you can use. Okay. That's great, but it's also terrible for, you know, attendance for these clubs. Don't be stressed about it.
Yeah, it was like, should be like 2 days before, and then you'll see attendance. So, getting frustrated. It was good, but like, that's something different. I guess not very much, but just.
Well, yeah, that's what I'm saying. So you might do that. Size. Well, I'm ready. You know, you rank this. No, because there's no. As far as array is yeah. And then I get that. I mean, this is good. I guess that's my point. This works because it's true one. It's three. Like it's entirely possible that for some data type it returns 0, and that is false. Yeah, and you don't want that. So
If we press the questions, we just do
like
5 or so minutes per question, and then you just go through the answers. You don't necessarily have to type it out yourself.
Yeah, because what I was thinking was if people want